So let's begin. So welcome. So this is the third bit of this chapter, which is the first law of thermodynamics. And so what's going on here? It's an attempt to link together the heat and work. And I remember being really confused about this. And what it really is like, the analogy is your bank account. You have two ways of getting money into and out of your bank account. You can go to an ATM, and you can use the ATM, and you can go to inside and see the teller. And two different ways, and you just got to make sure you count what you're doing on both ways. You're not stunned if you go to the ATM and you put in $100, but your bank account goes down by $900 because you went to the teller and you took out $1,000. I mean, it's like you go, oh yeah, I did this there and I did that there. It's like, but you can do, the analogy is, heating and squashing. So imagine a gas cylinder. You can heat the gas cylinder, you can squash the gas cylinder. You can heat the gas cylinder, you can expand the gas cylinder. You can squash it and cool it. You can do these different things. So work is, the way I'm picturing it, a bit like going inside and talking to the teller at the window, and heat is a bit like going to the ATM. And what gets people confused is I can put a Bunsen burner under a piston of gas, and I can expand the gas so much that I'm taking more energy out than I'm putting in with the Bunsen burner. So my net energy inside goes down, so my temperature goes down. They go, oh, you got a Bunsen burner, how can your temperature go down? Temperature goes up if your Bunsen burner's adding energy to the system. If your Bunsen burner's adding an insufficient amount of energy to the system, and you're taking energy out by expansion that's more than you're adding with the Bunsen burner, the net effect is the temperature goes down. Just like, yeah, you put money into the ATM and your bank account should go up. But if you draw more money out via the window, your bank account's going to go down. So we're not looking at the complete picture. And again, this is I must confess, in this section and in other sections of thermodynamics, it's almost like they're deliberately not saying things. They don't emphasize the fact that internal energy or thermal energy is linked to temperature. So when temperature goes up, the total amount of internal energy is going up. When temperature goes down, the total amount of internal energy goes down. That's one thing they don't link. And there's another thing coming up on this next bit. So we've got to somehow summarize what we do at the teller and what we do at the ATM machine. We just add them together. Well, we've got to summarize what we do in heat and what we do in work, and we just add them together. What makes it a little confusing, we all know that heat is positive. You put a Bunsen burner on your gas and you put energy in, so let's call that positive. Yeah? What do we call expansion? When the gas expands. Do I call that positive or do I call that negative? And it turns out that when you expand the gas, you're taking energy out of the gas. So expansion of gas is negative. That's not so obvious. What makes it even worse is if you have an old version of a textbook, including the one, Survey, physicists used to, and some still do, have expansion the other way around. Well, yeah, they also have the equation the other way around. So two wrongs made a right, Chemists look at the expansion from the gases point of view, whereas physicists and engineers tend to look at the expansion from the machines, the engine's point of view. And pushing on an engine is putting work into the engine, so that's a positive thing, Well, okay, positive W means I'm just, to make this thing work, I've got to have a negative sign in front of it because, it'll work out. So you'll find in many textbooks, in my old notes, and what's a bit more embarrassing is in my homeworks probably to this day, you see delta E int. is equal to Q minus W. And then expansion is positive, whereas delta E internal is equal to Q plus W, expansion is negative. That's all it is. You're just swapping around the nomenclature. And it only changed, I think, about a year ago in our textbook. You know, this last edition, I think, is the time when it changed. So I swear, if you look at old textbooks, you'll find the opposite equation down, and you know, even in Selwyn Font. I think I did my homework doing that way. So eventually I'll change it, but I'll always be a little bit concerned because I'm sure there are lots of books out there that have the top equation rather than the bottom equation. So the principle is you get to understand what you're doing, and you can do it. So a typical question, let me just see, do I have a typical question in here? Not so much. So let me just quickly do a typical question. So a typical question might be, what are you saying to me? Check online solutions. Sharp pen has stopped working. Why would you stop working? Oh, come on. Stop playing around. Let's try you one more time before I give up. Autosave. Load it now. Yes. Don't give me much options. And then let's go to the next page. Wait a moment, please. Oh, so you're not stopped working. You're just reluctant to work. Sorry. Okay. So, typical question. Typical question might be, you have a cylinder of gas, and you put a Bunsen burner on here, and you add 90 joules of heat. Q is equal to 90 joules. Bunsen burner, so it's a positive 90 joule. If I had ice pack, negative Q. Yeah. Gas expands. Gas expands, doing, so expands, doing 40 joules of work. So notice I don't give you the sign for that. Okay. So what is my change in my internal energy? Thermal energy, the energy inside the gas. What is my change in it? I say, well, delta E int, let's do it the new way, is equal to Q in over epsilon, Q plus W. Doing something completely different. This is the new way, and so I say, oh, delta E int is equal to Q. There's no problem with that. It's a plus 90 add. Now, in this case, expansion is negative. So that's going to be a minus 40, which makes plus 50 joules. My internal energy increased, which means my temperature of my gas increased. Yeah, I don't know how much by, but I know my temperature of my gas increased because my internal energy increased. That's the new way, and the old way is delta E int is equal to Q minus W. Delta E int is equal to plus 90 minus expansion in this extreme, in this terminology is positive, plus 40, which again gives me plus 50 joules. So either way, they get the right answer. It's just there's two different ways of looking at it. And I think actually the reason I just put up this section for the homework, and the reason why the section of the homework wasn't there was because I was trying to sort out this issue, I think I do it both ways in the examples that I show. You take your choice. Okay. Cool. Okay. So not so bad. Just a bit of terminology and etc. etc. It's not so bad at all. Let's go here. Okay, so that's that bit. You can steer, I don't know if that's spelled right, you can steer your way around a PVT diagram. Now, so we like this to show this with gases because it shows it, well, expansion's obvious and all that kind of stuff. You know. So then people start playing with PV diagrams. And they're really PVT diagrams, but they don't call them PVT diagrams. They call them PV diagrams, P and V. But as we know from Boyle's law, PV equals a constant for a given temperature. Change the temperature, and you get a different constant. Change the temperature, and you get a different constant. Change the temperature, and you get a different constant. This is T low, and this is T high. So superimposed on this, I'm going to change colour of pen so that it's not so confusing. So superimposed on this, we should have a whole bunch of, isotherms. And they're just never drawn in. And again, it took me the longest time before I realized, when I go from a pressure and a volume there, and I go to a pressure and a volume there, I've not just changed the pressure, but I have decreased the temperature. Because to live here, you've got to be on that isotherm, and to live here, you've got to be on that isotherm. There's no way around it. The only way, how do you get a gas to have the same pressure, the same volume, but a different pressure? You cool it. You reduce its temperature. So there's temperature information going on here without it being obvious to me anyway. How do I increase my volume while maintaining the same pressure? If I increase my volume, the temperature wants to go down. The pressure wants to go down, expanding the gas. Pressure goes down. I put heat in. I increase its temperature. So I can then start to intelligently interpret these things. What's the conundrum that's set up? What they say is, look, you start off at that physical situation. You're at a certain pressure, temperature, and volume. And in each case, we end up at that physical situation. We're at a different pressure, temperature, and volume. Okay. Well, if I look at the work done, remember that work equals force times displacement times the angle between them. Let's say they're in straight line. So force times displacement. And, pressure is force. Let's multiply by area and divide by area, which equals force, displacement, area over area. Did nothing, just multiplied by 1, yeah? Force divided by area is pressure, and distance multiplied by area is volume. Got to change something. It's P delta V. Remember how here you had to have a force and it had to move through a distance? Now you've got a pressure and it's got to change the volume. You've got to change the volume. So there's an alternative way of looking at work done. And if I look at this, the pressure times the change in volume, pressure is going to change, the integration of the pressure times the change in volume is the area under the graph. So we can actually look at these graphs and we say how much work was done. And what we see is there's different amounts of work was done. And I remember, when I was in this class, my instructor kind of going, how can that be? You have different amounts of work done, and yet you start at the same place and you end at the same place. How can you start at the same place and end at the same place, and yet have different amounts of work done in this journey, Because the journey consists of two bits. There's the heat part and the work part, and we're only talking about the work part. It's like saying, how can my bank account, 3 people, our bank account start at $90 and it ends at $30, and yet you took out $20 through the ATM, I took out $50 through the ATM, and he took out $60 through the ATM. How can this be? Well, because we also went inside and played around with our bank accounts through the teller. So it's almost like they're deliberately hiding one parameter and seeing, can you think in terms of these three parameters? And it'd be nice if somewhere at the book it said, think in terms of these three parameters, but it never seemed to do that. It just kind of showed you it. So this is no big deal. What happens is, yeah, I do a different amount of work, but I put in or take out different amounts of heat. And I steer myself to the final answer. So that drove me crazy until I recognized what was going on, and then it just became much simpler. Then it was like, oh, I get it. So, how much work is done by gas in this expansion? So I'm looking down here. So how much work is done by gas in this expansion? And work is equal to P, well, the integral, if you like, P delta V, or dV. So I look at this, it's a nice constant pressure. So that's going to be 5 multiplied by my change in volume, which is 4 minus 1, which equals 15 joules. And let's say it doesn't go linearly. I've got to give you the equation. So then I say, well, work is equal to the integral of P dV, which equals the integral of my P. P is 6 over V squared dV, which equals the integral of 6V to the minus 2 dV. What do we do with integration? We say increase the thing by 1 and put it in the denominator, yeah? So that goes to 6V to the minus 1. It's going to be a minus that, which equals minus 6 over V. Did I do that right? I think I did that right. Yep. Yep. So then I go, okay, and where's my limits? My limits are 1 to 4, 1 to 4. So this is going to be minus 6 over 4. And then we have minus, and we have minus 6 over 1. So work is equal to minus 1.5 minus 6, which equals plus, what, 4.5 joules. And yes, there, 4.5 joules. It's, whatever, yeah. So I can do the calculus way, I can give you the graphical way. Ironic thing is, more people who get the calculus way right than get the graphical way, because it's a long time since we did, do it areas under a graph. So make sure you can do both. So quite accessible, just new terminology, and there's a little bit of shenanigans going on about them, deliberately not telling you things. Terminology. Again, I was so focused on what I considered, tricky problems that I didn't bother doing the stuff about learning the language, and paid a heck of a price for it, because when I actually got into the test, I had problems with the questions because I didn't understand what it was asking, because they used terminology. So there's basically 4 different changes we can have with a PV diagram. We can have isothermal change. What an isothermal change means is that you stay at whatever temperature you're at. If my temperature does not change, does my internal energy change? No. If my temperature does not change, then my internal energy does not change, because temperature is the average kinetic energy per particle, and if the temperature is not changed, then the average kinetic energy per particle is not changed. Got the same number of particles with the same average value, got the same internal energy. And that's a link that's, again, not emphasized, but it's a really important link. So if I look at my first law, delta E int equals Q plus W, delta E int, my change in internal energy, must equal 0 for an isothermal change. Now, what would my work be? Well, my work would be whatever's under the curve, and you have to be given an expression for that curve. That's up to me to give you the expression. But you integrate it. If I want the work, you integrate it. Next, isobaric, bar pressure scale, isobaric. Isobaric means you stay at the same pressure. If I stay at the same pressure, then, okay, yeah, my temperature changes, so my internal energy changes, and certainly my Q changes, because I'm going, it's certainly doing work, so there's no insights in this. The only thing I can say is that my work is a simple function. It's just going to be pressure times the change in volume. I don't have to integrate particularly. I mean, you know, it's an easy integral. Just multiply the pressure times the change in volume, yeah, to work out the area. Whereas here I have to actually do real integration. Here it's a constant function, so a lot easier. That's the only thing you can say. Remember, it's pressure times change in volume. It's not volume times change in pressure. Okay? Like, I can push against that wall as hard as I like. If my hand doesn't move, if the force doesn't move, there's no work done. Same thing with this. There's got to be a volume change for work to be done. Let's look at it when there's constant volume. It says constant volume. Well, my expression is still that. I'm changing temperature, so yeah, I've got a change in internal energy. But what I do know about this is there's no work done. There's no area under that graph. So that means W equals 0. So, work equals 0, and delta E equals Q. And this next one is the one that I struggle mostly with, and that's adiabatic. And all adiabatic means is heat is 0. Change in heat. Basically, heat in, heat out. Not change in heat, but heat is 0. You don't allow heat in, you don't allow heat out. Calorimeter would do that. A nice insulated glass would do that. If you don't have an insulated glass, if you just do something quickly so that you don't have time to get the heat out. You change it and you take your reading, you know. Temperature before, temperature after. It's not a time to change. Then you can approximate an adiabatic change. Important technologies like automobile engines, things happen quickly, so it approximates adiabatic change in there. You got to be really careful or really quick. With Boyle's law, we wanted constant temperature, so the way we did it was we were really slow in moving our syringe. Tried not to hold it and all that kind of stuff. So people get the idea it's a curve, but they get it confused with an isothermal curve, with a temperature curve. So I want you to be clear on this. When I do, this is a compression going that direction. When I do an adiabatic compression, I squish on the piston. What happens is my temperature goes up. Yeah, my temperature goes up. And if there was time for that energy to escape, my temperature would come back down to room temperature or whatever it was to begin with. So the fact about adiabatic is there's not time, or there's insulated cladding, so it can't escape. So by very definition, an adiabatic expansion involves a temperature rise. And so it must inevitably start off on a low isotherm and end up on a higher isotherm. It's got to go steeper than the isothermal curves. And by definition, when I expand a volume of gas adiabatically, what happens is there's no time for heat to come in to maintain the same temperature, and so the temperature falls. And so I start off on a higher isotherm and I end up on a lower temperature isotherm. So it's a steeper curve. I'd like you, not above asking you to draw a typical isobaric, isothermal, isobaric, isovolumetric, or adiabatic curve. I'll give you a starting point and say, draw me one of these. Nice conceptual question. And I want to see that in this case that it actually goes our equation, well, what can we say about this? Really, I mean, all we can say is Q is 0 in this case. So our equation simplifies. So in a few cases, our equation simplifies, and in some cases it doesn't. So just Don't not be able to do this problem because you don't remember what isobaric is. It's like, it's a shame if you can't do the problem because of that. So we know that I can work out the area, I can work out the work done on or by the gas, putting money in or taking money out at the ATM. I can figure that out by the area under the curve. So I have two sections here where what's happening is my volume is decreasing. So that is squishing on the gas. So by our new terminology, we would call that positive. Yeah, by our new terminology. The old terminology, call that negative. Yes, yeah. By our new terminology, we call that positive. That bit there is positive work. And this is an expansion of the gas, and by our old terminology, we'd call that positive work because expansion was positive. In our new terminology, we call that negative work. Doesn't really matter. There's a difference. One's positive, one's negative. You want to know the net work done on or by the gas, get the area that's in between the two. Now, this represents energy that is available to a machine. And I'm driving it by, let's have a look. I have a machine where I am getting energy out of the system, and I start and end at the same point. So my delta E int equals 0 joules for the entire cycle. Yep. But my delta E int equals Q plus W. And so 0 equals Q plus W, so Q is equal to minus W. So the sign is, again, I think I know why the engineers and physicists like to have the negative sign for the positive sign for expansion, because it just would give you a positive in the traditional way. But can you see how the amount of work you get out is numerically equal to the amount of heat you put into the system? This is amazing. This is a way of using heat to get work. We're all familiar with using work to get heat. You just rub your hands together. That's using work to get heat. That's unavoidable. When you're driving your car down the road, you're using gasoline to cause work that heats up the air and the road. That's what you pay for your gasoline, is basically causing heat. Also takes you to work, but life doesn't care if you go to work. Nature is not blessed by the fact that you happen to go to work. It's just, all right, what you did was you energetically turned chemical energy into thermal energy, and then thermal energy into mechanical energy, and then mechanical energy into thermal energy. From an energy point of view, you might as well just burn that gasoline in the back of your yard. Same effect as far as the world's concerned. You've been at work is just coincidental. So it's kind of easy, unavoidable to have work going to heat because that's friction. But going the other way around, actually doing the first part of that, getting the heat to go to work, that's the clever bit. And they didn't figure out how to do that until the 1820s, 1830s. Steam engine, etc. So if I want to know how much energy is in the system, I simply just work out what the energy is inside what the area of that situation is. And we'll get to that actually in the last chapter if we get to it, when we talk about heat engines. 3 little bits are left on this, and that is basically conduction, convection, and radiation. Conduction. So first of all, power. Power is the amount of energy per time, per second. Joules per second. So that's my joules per second, and that's my power. Not pressure, power. And here's a rod of material, and I think we can intuitively get this. The bigger the area, the more little windows for the energy to go through each second. So I would expect my area to be on top. And the bigger the temperature difference means there's a bigger driving force. So I would expect my temperature difference to be on top. And the further those temperature differences are apart, imagine it was here to the other side of the universe, you get very little energy flow, but across a plane of glass you get a lot of energy transfer. So I'd expect my difference in position, I'm calling it delta x here, I call it dx here, I call it delta x there. You know, if everything is uniform, this simplifies to that. Yeah, and that's when you're going to be asked the question more in, at this level of course, you're going to have to be asked the question more in this terminology than this terminology. I suppose I could give you a function or somehow and have you do a changing thing, but we're going to assume a nice uniform situation. You can figure that out really. What you wouldn't know about is how to get the numbers to work out, and that's where the constant proportionality comes in. And this is called the coefficient of thermal conductivity. It's just math. Give you one temperature, give you the other temperature, give you a separation, give you an area, give you a K, ask you what power is dissipated, ask you what energy per second flows down the rod. I can confuse some people by asking how much energy flows down the rod in 5 minutes, because they kind of learn that P equals, and they forget that P equals Q over delta T. Well, if you want to know the energy in a given time, you just go Q is equal to P delta T, which equals Ka delta big T over delta X times delta little t, meaning change in time. People just forget that. And then the other thing is, if they remember that, they'll put in 5 because it says 5 minutes. Like I would ever give you the direct UL, that I would not ever give you the wrong units to put in. Clearly I'm going to test that. You know, do you know to change the units to SI units? I'm constantly drumming on that beat because that's vital. Because if you put 5 minutes in rather than 300 minutes in, then you are 60 times the wrong answer. And that's a big deal. That's not a slip. That's 60 times the wrong answer. So watch out for that. Convection, that's, you've seen the ripples over the hot road where the air gets less dense and so its refractive index changes and so, you've been swimming out in the ocean and you've swum over some areas and suddenly there's like cold seawater around you. Not freezing, but cool, and then you're swimming and it's warm again and it's like, whoa, what happened? You look down, there's usually a different coloration in the seabed, maybe the seaweed or not seaweed, and you get these convections. My family, London is level. Where is London level with in the United States or Canada? What city or what geographical feature is it level? Is London level with Miami? No, certainly not. Okay. Turns out Athens is level with New York. Athens. Sun-blessed Athens is level with New York. London is level with not the very bottom, but in the bottom region of the Hudson Bay. It is way up there. If you just go on latitude, we should all be frozen, we should be Canadians just digging ourselves out every 2 weeks and all that. And yeah, I grew up and I'd get excited if there was like that much snow. Boston gets more snow than Britain got. I mean, it was like amazing. Why? because there's this thing called the Gulf Stream, which goes basically from the Caribbean all the way up to Britain and Scandinavia and all that. Norway has much better weather than it should have. And so I just moved from one end of the Gulf Stream to the other. It's kind of nice, really. I picked the good end, I think. So you can visualize it. Mathematically, it's incredibly hard to describe. Well, using traditional mathematical techniques, incredibly hard to decide because it is not linear. It basically follows the chaos theory idea that a small change at the beginning will make a big change at the end. So it's like turbulent flow, like we mentioned in fluid flow. So what do? We keep away from it. We just, no equation in this. There actually is an equation if you look back at the Hewitt book. If you did conceptual physics, Hewitt has an equation for it. But the traditional physics, the canon of general physics is that it's not included. So we just know it's there and be able to define it. So how would I define conductivity? What's my visualization? There's a fire, there's a pond. We want to put the fire out. We all have a bucket. We form two lines. In conduction, one line is passing bucket full of water down the line and throwing it on the fire. And the second line is passing the empty bucket back again. So my job is just to pass a full bucket, and pass a full bucket, and pass a full bucket as quickly as possible. And somebody else's job is to pass an empty bucket, and pass an empty bucket, and pass an empty bucket. And it's only the person near the fire who takes a bucket and throws it on, and takes a bucket and throws it on, takes a bucket and throws it on. And the person at this end is always just taking empty buckets and filling them, and taking empty buckets and filling them. It's very ordered, very specialized. No people move past each other once it's set up. That's like conduction. The energy is passed from atom to atom, but the atoms don't move past each other. Compare that with our situation where we all say, we've all got a bucket. We all run to the pond, get a bucket full of water. We all run back again and throw it on the fire. We all run to the pond. And we're running round each other and bumping into each other, and it's chaos. It still gets the job done, but it's chaos. And maybe that chaos is going to lead to knots of people which will be less efficient than if we had two lines. And maybe there'd be an instant or two when it would be more efficient. But it's two different ways of doing it. So mathematically describing the efficiency is for the chaos is very hard. There's a fascinating program. It's called The Code. It's done by a guy called DeSoto, I think it is. I'm not sure that's right. I can't remember the guy's name. English guy. And he takes like 6 bits of math and shows how every day you need to use math in lots of different things. And he describes actually just people moving through cities, which is somewhat chaotic. You kind of like, you don't want to bump into people, so you're steering via them. It's kind of like you're affected by them, even though you don't bounce into them, but you're affected by them. And so I remember when I was in college, one of the universities that they just built was famous because they did not put paths in when they first built the college. They just let the first 2 years students and faculty use the place. Then they look at where all the grass was worn down, and they put paths in where the grass was worn down. Rather than those walking around, which is like people start cutting the corner, they let them cut the corner and then put the paths in. So people are kind of interested in that kind of technology, really. They started looking at Grand Central Station and just how do people, because there's 15 doors and 15 doors and, people are going different places and they've all got to go through this common space. And it turns out that counterintuitively, if you put a barrier in the middle of an open space, And they put an information booth in the middle of Grand Central Station. And they were clocking how long it takes people to transverse this space and find where they want to go. What they found was, by putting the barrier in, they reduced the time of transit on average. How can putting a barrier in make it more efficient? And it was actually people were kind of like using rather than kind of crossing like this and having to wait or slow down or speed up, whatever, because it was circular, they tended to use it like a roundabout, like a circle. And it was much more, it was not much more, it was like 7% better. But I just found that program fascinating. It was kind of really cool. So it's not that there's nothing can be done, it's just it's not in our canon, it's not what we talk about. And the last one is radiation. That is not meaning radioactive. Radioactivity radiates, but light radiates. Sound radiates. We don't tend to call it radiating much, but it goes out in all directions. And so imagine a sphere. And, well, I would expect the energy per second leaving the sphere to depend upon the area. So put the area on top. Now, there's different issues. That's a black board, and that's a white wall. And it turns out that the white wall is a better reflector than the blackboard. Yep. The white wall does not let energy, photons, in very easily. It bounces them back. That's why it looks pretty well white. If it's not a good acceptor of photons, it's not a good emitter of photons. So it's not a good radiator of photons. The blackboard, the reason why it looks black is because it accepts all the colours of light that are bouncing on it readily. So it's not a good reflector, which means it's a good absorber of radiant energy. If it's a good absorber, if the gates are open to let you in, they're also open to let you out. So it's also a good radiator of energy. So we've got to somehow characterize the difference in the willingness of the object to radiate. Surface finish, matte is better than glossy, black is better than white. We've got to take that into account. And we use a figure of merit. It goes from 0 for basically no emissivity to 1 for complete emissivity. So that's what this is. This is our eta, which is our 0 to 1. Clearly it depends on temperature. If you have more temperature, you have more energy, so there's going to be more. Well, you don't necessarily know that, but it does. What's not obvious is it's t to the 4th. How many times do we see a something to the 4th in a physics class? It's phenomenal. That's empirical. I can't prove it to you mathematically, but that's empirical. And then we have a number to make all the numbers come out right. And this is called our Stefan Boltzmann constant. It's basically a fudge factor. Notice t to the 4th. If I do a comparison, so I go that new, that new, that new, t new to the 4th, over that old, t old to the 4th. Well, let's say I don't change those two. Let's say I don't change those two. Let's say I don't change those two. Let's say I just change the temperature of my object. Then my new power over my old power, if I double the temperature, so T was 1 and now it's 2. 2 2s are 4, 2 4s are 8, 2 8s are 16. So that would be 16 for, so 16 times the power for 2 times the absolute temperature, not the absolute temperature. If I had 10 times the absolute temperature, then it would be 10 times 10 is 100 times 10 is 1,000. 10,000 times the power. 10,000 times the power emitted, 10,000 times the power needed to maintain that temperature. So doubling the absolute temperature of something is very expensive. It's not twice the amount of energy needed in fuel, it's 16 times the amount of energy needed in fuel. Where this really shows itself, actually, is in, really shows up in stars, for example. It turns out that the temperature of a star depends upon its structure, and the bigger the star, the hotter the star. And big stars that we notice are blue stars, and stars we don't notice, cool stars that we don't notice so much, smaller stars, oh, I've got to be careful about that, are reddish stars. I've got to be careful about saying small stars are reddish because a red giant is red, you know. That's a star that's blowing up at the end. But if you take two stars in the middle of their lives, and one's blue and one's red, you're consuming, let's say the temperatures kind of go from about, our sun is about 6,000 to a typical blue sky might be 30,000, so it's a factor of 5. So that means factor of 5 would be 5 times 5 is 25 times 5 is 125 times 5 is 750 times the amount of fuel per second burned in the blue star versus the red star. And it turns out that you don't have, the star is not 750 times more massive. So you don't have that much more fuel. So it burns out quicker. So the blue stars burn out quicker than the red stars. And you can see that actually when they look at the solar system, when they look at the galaxy, they see the plane of the galaxy where the Milky Way is, then they see these clusters, globular clusters they're called. And they don't go in a circle. They basically just go, you know, backwards and forwards through the middle of the galaxy. They're gravitationally bound, but they're not rotationally. They don't have this circular motion. There's no blue stars in them. What they reckon is these were the first stars that were produced before the circular motion in the galaxy formed. These were formed first, so they never got that circular motion bit. And the reason why there's no blue stars is because they're old. And the blue stars have all burned out. They were there originally. It's just star stuff. Makes blue stars, makes red stars. It's just like, you know, taking powder and throwing it. You get big clumps and little clumps. No reason to think that there's some difference in how much of it is red and how much of it is blue. It's same old, same old. But they're all gone, and they're gone because they're old. So it's kind of interesting. Rod is 2 meters long. It has a cross-sectional area. So 2 meters long. Cross-sectional area, 20 centimeters squared. One end is at 15 degrees C. The other end is at 30 degrees C. Power goes in that direction. Coefficient of thermal conductivity is 4 joules per degree C meter second. How much energy conducts along the rod in 4 minutes? P is equal to Q over delta little t, which equals K, A, delta t over delta x. So Q is equal to K, A, delta t, big T, over delta x. Take this time to the other side, so I get multiplied by little t. Q is equal to, well, that's in standard units, so that's 4. Oh, okay. And then we have our A. Our A is going to be, we're going to do this, 20 times 10 to the minus 4, because we've got to work in square meters. Delta T over delta X, delta T over delta X. It turns out delta T is a difference in temperature. So it turns out if I go 30 minus 15, is equal to, well, that's going to be 15. Bad teaching, because I got the same number coming up twice. Should have really picked two different numbers. If I take 30 plus 273 minus 15 plus 273, so I'm in Kelvin, the answer is 15 Kelvin. Because 15 Kelvin is the same as 15 degrees C. The temperature difference of 15 Kelvin is the same as the temperature difference of 15 degrees C. So it turns out I can put this in just 15 for that temperature. Whoa, for that temperature difference. My delta X will be 2 meters. Now my delta T is 4 minutes. So that's going to be 4 times 60. Yeah. Math. Did I bring my calculator? Man, hopefully it's in my box. I've been very bad about pulling my calculator just out of my box. So we just go basically 4 times 20 second EE to the minus 4, enter, times 15 equals, times 4 equals, times 60 equals, divided by 2 equals. I'm getting 14.4. So not so bad. I can throw curves at you. I suppose I could give you the radius and tell you it's circular, and then have you work out the area. I suppose I could give you a square rod and give you the side, length of side. I could give you a rectangular rod and give you the width, and I could give you a triangle. I can mess with the area a bit. Can't really do much about the length, about changing its units, really. Temperature difference is temperature difference. Time, I can give you in seconds, give you in minutes. Not ask you for time, I ask you for power. I can play with that. I could do a ratio on this. New versus old, you know. I could do a graph. I could say, plot me the energy, or this, let's say, plot me the power versus the length of the rod, or everything else kept constant. And you go, there's the power, and there's the length of the rod. That's an inverse relationship. I can do that. Yeah. Same old skills. 200 degrees C sphere so I'm a sphere, and my emissivity is 0.3, so quite absorbing. Has a radius, not so absorbing, not so emitting. Radius of 4 meters, so R is equal to 4 meters. How much power does it dissipate? Power in so much time? No, power is just a rate per time. It's joules per second. So I don't have to give you the time on this. I can put the power it dissipates. So I go power, which equals Q over delta T. Why do I put that down? Because I want to keep reminding myself of that. Is equal to sigma A E eta T to the 4th. So power is equal to sigma. The numbers here, in a test, you would leave the sigma as the sigma. Life's too short. We'll leave it as a sigma. A is equal to, radius, 4 pi r squared. You expected to know that. It's a sphere, surface area of a sphere. Eta is 0.3 T to the 4th. So power is equal to sigma 4 pi. My R was 4 meters, 4 squared, 0.3. Now, this T of course equals 200 degrees C. T equals 473 K, because you've got to be in Kelvin for this. If you get used to putting down TK, then you know it's got to be in Kelvin. And so this is 473 to the 4th. So P is equal to 4 times pi, enter, times 16, enter, times 0.3, enter, times, parenthesis, 473 caret 4, close parenthesis, enter. And I am getting 3 times 10 to the 12. You've got to look at the end to make sure there's no power or what the power is. And that would be in watts, or sigma watts, because we didn't work out what sigma was. If I want to just do that quickly, I will go times 5.7 second EE to the minus 8, and that would be not got my let's look at a light here, and that would be 172095. So this is 172095 watts. Big surface area, etc. Did I do that right? I guess I did, yeah. So sometimes in homework I will ask you to work out what the value is, and part of the reason for that, and I've got to be more pointed about it, part of the reason for that is I want you to get an idea for how big these effects are. I'm not doing it very well at the moment, I'm just putting down, work out the numbers, but there's a certain advantage in knowing that a Newton a meter is a joule and a Newton meter per second is a watt, and being able to visualize it. And it'd be nice if I did something like this and said take 100 degrees C tub of stuff, maybe 1 meter radius. How much energy would that radiate? If it's perfectly black, how much energy would that radiate? And just figure it out. So you have a feel for how much energy you get off a radiator.